All right, so we've had some pretty heavy stuff this week, and here we're going to have some fun with some elementary truths of quantum mechanics. I sort of heard that decoherence is becoming one of your buzzwords, so I thought I was very pleased when Laura invited me to talk and to review some of the stuff we've been doing over many years in this field, and maybe some of the insights or things that we have seen will be helpful, and only at the very end will I have something relevant to space-time or relativity. I call it quantum damping because this is the name that we originally gave to it with my friend Robert Harris. I don't know if anybody knows him. He's a physical chemist at Berkeley, Bobby Harris, and you'll see in a second why it was good that he was a physical chemist. So the best way to start, I think, is the historical ordering of how this developed. And the first thing was that in this work with Bobby, we found something which is too good to be true. And like most things, when something is too good to be true, it is too good to be true. And this was a way of measuring incredibly small energies. And the point was that back in the 1970s, we were looking for neutral currents. Now, this was one of the unusual or strong signs of the weak interaction standard model that you would have, in contrast to some other models, a direct interaction with parity violation between an electron and a nucleon or a nucleus. Sort of like now we say Z0 exchange. It would be like the Coulomb force, more or less, but short-ranged, and would have parity violation. So Bobby and I were thinking, well, how can we detect this small parity violation? And one thought that occurs to you is, if you're talking about parity, of course, you have in physical chemistry left and right isomers, different chiral states of the same thing. And so our guesstimate of the energy difference with this sought-for neutral current would be extremely small because it's weak interaction, short range. And we got 10 to the minus 15th electron volts or less. Now, or in time units, this is the inverse of 1 second or longer. So you could hope that, let's say, take some molecular levels in a left or a right isomer of the same stuff and see if these energies were slightly different by spectroscopy. But this is hopeless. You will never see something so small. And Bobby and I were thinking about, well, how can we possibly see this? And now, being an old admirer of the famous K0 oscillations, we got the idea, well, you can have an analogy with parity as the quantum number, as you have with K0 oscillations, which you have with strangeness. That is, you have two degenerate states, left and right states of a chiral isomer, and there should be some oscillations between them. So, for example, the Hamiltonian of such a system would look like this in the basis of left and right states. There's a tunneling energy, which is conventional, although difficult to calculate in practical cases. And the parity violation would be this epsilon, which would mean that the left and the right isomer would have slightly different energies. And this, as I say, this epsilon is 10 to the minus 15th electron volts or less. Well, but how are you going to see this tiny epsilon? Well, it's easy. So here's the simplest example you can think of the chiral molecule. You can have, for example, an ammonia-like structure. Hey, my laser stopped working. Where is it? Oh, yeah, there it is. So you can have an ammonia-like structure where the nitrogen is above or below the plane of the hydrogen atoms. A slight technical point is you have to make the hydrogen atoms different for it to really have a hand in this, because you have to be able to go around one way or go around the other way. But this is practically the simplest thing you can think of for a chiral molecule. The trouble is that the nitrogen oscillations, which this is the ammonia maser, which you may have heard of. If you change the nitrogen to phosphorus or some heavier group, you can slow down the oscillations because it's a tunneling process. So you put in something heavier. And you can get this to be on the order of the 1 second or so that we need. So it's conceivable you could do this with substituting something for the nitrogen. So it's a tunneling problem between the left and the right isomer. And if both potential whales are exactly the same depth, then there's no parity violation. But if they're slightly different, we could hope to see them. And the point is, since the tunneling energy is also so small, let's say 1 second inverse, you can compare your small parity violation energy with the small tunneling energy, and maybe the ratio gives something interesting. And in fact, here it is. Let's say you started with a left isomer, and you let it oscillate. If parity is conserved, there will be symmetric oscillations because the left and the right isomer are exactly the same. But if parity is not conserved, you will have these asymmetric oscillations. This axis is the amount of left or right. So it's easy. You start off with a beam of left isomers. You let them fly along. 1 second later, there's the detector here, and you see how often it oscillates into the right isomer. Nothing to it. Except this is obviously too good to be true. Something must be wrong as a practical matter. Why doesn't this work? Well, after some thought, we realized there's an elementary reason why it doesn't work, which is that even in the best vacuum, this molecule will hit something within 1 second. Even some residual gas of the best vacuum will lead to some collisions. I don't know about, haven't looked at it for nowadays with the vacuums you get nowadays, but I think even with the best vacuums you can make now, this thing will hit something within 1 second. So we were faced with a problem. If we want to really pursue this as a practical matter, how do you treat these collisions? And so you need some kind of quasi-scientific theory of the decoherence induced by hitting something. So when the wave function is oscillating along, what do you do when it hits something? Do you stop the clock and start the wave function again? How do you know what state it was in? It's quite confusing once you think about this. And of course, there's a real practical question. We're proposing an actual experiment. We want to know what's going to be seen at this end if you cannot avoid the collisions. Well, there's a tool in quantum mechanics for dealing with such problems, and that's the density matrix. And so what you need to do is to apply your ideas and intuition to the density matrix. So we have the simplest system you can think of for the density matrix, a 2x2 a two-state system or a 2x2 density matrix, which you can characterize, which you can write like this. And you can write the density matrix in this simple case as a polarization vector times the Pauli matrices. And as time goes on, this polarization vector will rotate around. Being a two-state system, it's isomorphic to a spin, and it's easy to visualize when you look at what this polarization vector is doing. So here's a picture. You see, there's the internal Hamiltonian, which I just showed you, which you can view as a sort of magnetic field, this V, which in the case I wrote down would be the Z component would be the parity violation energy, and the X component would be the tunneling energy. And at this elementary level where there's no external world, this polarization vector is rotating around the V, the pseudo-magnetic field. And I'm sure you've all shown this when you've taught first class in quantum mechanics. And if you apply the equations of motion for the density matrix, you will find that indeed P dot, P is rotating around the pseudo-magnetic field. Now, one important thing about this is that P does not change its length, right? If you take the scalar product of P times P dot, it's zero because of the cross product. So this vector, the polarization vector of the density matrix is rotating around, but not changing its length. Even, as we'll see in some applications later, if the pseudo-magnetic field, if the V is moving, which arises in some problems, the P still stays of length 1. So we haven't yet got any decoherence. We've still got a pure state. This density matrix obeys rho squared equals rho. It's a pure state as long as the absolute size of P is 1. So now let's figure out how we're going to get P to change its length. Well, we have to introduce some external world. So let's imagine us embedding our chiral molecule or other system into some external world, and let's write the big wave function of the spin. So let's call these two states plus and minus of the spin variable into some big wave function characterized by some environment which with a lot of coordinates. Now, if you trace out the other coordinates, here's what the density matrix for the spin, for the two-state system looks like. You have diagonal elements which essentially tell you how much you've got of one state, let's say the left isomer, how much you've got of the other isomer, and an overlap between the wave functions connected with those two states in the rest of the world. See, taking the trace gives you the scalar product of this rest of the world wave function. Right? So what we're looking for as with the progress of time, how this overlap of the rest of the world wave function decreases with time as it becomes more correlated with the state of the spin. Let's imagine that immediately at time equals 0, when I threw the chiral molecule into the medium, the state of the rest of the world did not depend on the state of the spin. In other words, phi plus was equal to phi minus. So then obviously any things I do on the spin, any measurements or manipulations I do on the spin, will be coherent because the rest of the world doesn't care. The phi plus scalar product with itself will always be 1. But in the other extreme limit, where the phi plus and the phi minus, the rest of the world wave function, are orthogonal, then I can't get any interference when I measure something between the two states of the spin because the rest of the world will be orthogonal. There can't be any interference effects between these two states of the spin. So that's what I wrote here. That's the interpretation of this 2x2 density matrix. So to understand the development of the decoherence, or how this polarization vector Laura, you're here, great. To understand how this polarization vector is decreasing, we need some model of how the rest of the world is interacting with the spin, or with the chiral molecule. So here's what you do. Let's imagine that I divide the rest of the world, some other molecules or atoms or photons, into those which have not yet interacted with the spin and those that have. So here comes a molecule from the environment flying along, and it hits the molecule. And now we have to use the S matrix in the original Heisenberg sense. What is the S matrix? It turns an initial wave function into a final wave function. So if the, and it's important that I'm using S and not T, not the transition matrix, but the whole S matrix, including the 1 in the S matrix. That's the most important part of the S matrix. So it'll produce a different state of the environment according to whether it's interacting with the left or right isomer, or with the plus or minus state. So what is changing is that overlap in the overlap in the off-diagonal elements of the density matrix. So if you follow this thought of the off-diagonal elements of the density matrix, you see what's happening is that this is decreasing because S scattering on one isomer may be different than scattering on the other isomer. And if you work out what you get, you'll see there'll be some decreasing with a minus sign of the off-diagonal element, some decoherence being created per unit time if I have regular collisions with the isomer or the abstract spin. So if you work this out with the details, you get the following formula for. So we've now got a decoherence rate, how fast the off-diagonal elements are decreasing. And if you work out what I just said with some details, you get the final formula that the decoherence rate is this. It's the flux of incoming particles from the environment, imaginary I times something. This funny business with the imaginary I use this notation because it then makes the scattering amplitudes look like those you have in the textbook for ordinary scattering theory, times the following. 1 minus S dagger for the scattering on one isomer or one state times the scattering on the other state. This just follows from the thought if you look at what's happening to the decrease of this overlap. Now, this is a very amusing formula with all kinds of nice properties. One way of looking at it is that it's sort of the unitarity deficit in the interaction with the environment. See, this would, if the two states scattered exactly the same, so if you were in this interesting limit here, you would not get any decoherence. D would be 0, because then it would be purely unitary. You wouldn't have any unitarity deficit. This would be just 1 minus 1 equals 0 in this formula. So this is one of our first interesting observations for your delectation, that not all collisions stop the clock. You can have many collisions with your system, but unless the system reacts differently in the two states, there's no decoherence. So the vague feeling that every collision somehow restarts the clock is not actually true. It depends on the nature of the collision. And of course, maybe a zeroth order point is to say that this is real physics. There has to be some interaction. You can't decohere something by just thinking about it. I mean, something is really happening. There has to be a real non-trivial S matrix. And furthermore, the S matrix has to have the property, if you want decoherence, that the two scatterings are different. The two scattering amplitudes are different. And this has a real practical meaning. For example, one of the examples that Bobby and I worked out was that imagine I have my chiral molecules in a buffer gas of liquid helium at low temperature. We were trying to think of some way of containing it so you could do some of these experiments. Now, it turns out helium is a nice round atom, and at low temperature, helium atoms are moving very slowly. So most of the scatterings on the chiral molecule will actually be in the S wave. And so since S wave is spherically symmetric and the helium is nice and round, actually most scatterings will not be able to feel whether they're on the left or the right isomer. So we estimated that actually only, I think it was 1 in 10,000 or 1 in a million scatterings would actually decohere the isomer. I think this is one of the observations you should keep in mind in some of the folklore on these things, that not all scatterings, actually, not all interactions decohere. Let's look at the opposite limit, which is more like the usual idea. Let's say that one scattering, let's say on the left isomer, there's no scattering, and just the other one are scattering. Then if you work out this formula, in that case, you see I have 1 minus S of the plus scattering plus S matrix, and you remember 1 minus S is the T matrix, is the true usual scattering amplitude with an I and so on. And because of the way I define the I's here, you get by the optical theorem that indeed, in that case, the D is the scattering rate of the one which is interacting. There's a 1/2 here, which is sort of a quantum effect. So therefore, in this case, you get the naive idea that every scattering, in a sense, leads to some decoherence. And by the use of the optical theorem on the scattering matrix, where the imaginary part is the cross section. That's why I define the I's that way. And here you have the normal intuition in this limit that every scattering is decohering the system. And then, of course, you can imagine many intermediate situations between these two cases, and you have to get the phases and everything right. I've worked out some examples in some solid-state devices for this. Now, so what lessons do we have here? Well, first of all, the decoherence rate is the dissipative quantity. It's like it comes from the imaginary part of the scattering amplitude, and you need some dissipation going on. And this stuff is continually being rediscovered and sometimes messed up, and so on. And one of the things you should watch out is that if somebody's trying to sell you a decoherence process where there's no imaginary part of something, be suspicious. There's probably something wrong. And the point is, the real part actually also has a meaning. The real part of this quantity here, where I just took the imaginary part, the real part means the level shift of the isomers due to the interaction with the medium. If you look back at that density matrix formula, it leads to a phase factor for the two components of the density matrix, which means it's rotating, so it leads to an energy shift, but not a dissipation. One of the ways I got convinced at the time when we were doing this that we had the right formula is that if you do this with the real part, you indeed, there's this classical formula from optics, which also you say in neutron physics, for the index of refraction of a particle in a medium. And if you use our formula for the real part, you get the right formula for the index of refraction. But, okay, here we're mainly interested in the imaginary part, the dissipation. So doing this, you get the final formula for the evolution of this density matrix in terms of this polarization vector, which is like this: the rotation due to the internal Hamiltonian, and then the dissipation due to the interaction with the medium. And it's all incorporated in this parameter d for the dissipation. So this will lead to a shrinking of P, and you will have decoherence. And this will continually shrink with time. And with this formula, you can calculate how the chirality of the molecule is, how the density matrix is approaching the mixed state for molecules, how neutrinos oscillate in a medium, how states of a qubit are being washed out by decoherence, and so on. And I'll try to roughly talk about some of these things if I have time. So here's what a typical solution looks like for the rotation of that vector, which is precessing around the polarization vector. If I start it at time equals 0, it wants to oscillate, but then the decoherence starts affecting it and it damps out. This is a particularly useful case to show where the internal Hamiltonian and the d are about the same order of magnitude. And we've worked out many different examples. So, as you would expect, of course, this d is leading to a loss of coherence, or as you people like to say, information. And here's, for example, you can calculate the change of the entropy defined by rho log rho. And you find, indeed, that it's increasing rather. And one nice thing to note, as you would expect, the arrow of time came out right. That is that the d is leading to a positive quantity. This quantity on the right is intrinsically positive. The reason for that is my basic formula is the mismatch between two unitary operators, the unitarity deficit. This mismatch can never lead to anything, must lead to something less than 1. So that's why the d is, we've defined it, comes out such that you have d of a certain sign, which is positive, because the mismatch of unitary operator must be something less than 1. So now there are some amusing paradoxes connected with all this. And some of them, at first sight, were quite baffling. And the oldest and earliest one, which we understood in the beginning, which is still nice, you remember Hund's rule from atomic physics, something from the early days of molecules, I think, early days of quantum mechanics. So Hund, in the 1920s, asked himself, hey, how come when we look at molecules, we see the chiral states? You know, when Pasteur was scraping wine barrels and analyzing their optical activity, he found one kind of handedness for the organic molecules. And Hund, being one of the early quantum mechanicians, said this is wrong because we know when you have some tunneling between the two states, the true ground state is left plus or minus right. It's not the chiral state. So Hund answered himself by saying, oh, that's easy. If you calculate the tunneling time of a sugar molecule, it's longer than the age of any conceivable age of the universe. So it's just tunneling, but it takes an essentially infinite time from our point of view. But as you saw from my third page there with the little ammonia-like molecules, that's not always true. You can cook up some molecules where the tunneling time is seconds. So Hund's answer, well, right for biological molecules is not really the full answer. Well, in modern times, there's another answer, which is that the parity violation. You see, if I make the Z component of my internal Hamiltonian big enough compared to the tunneling time, the polarization vector will be stuck in the polar direction, and it'll just do some tiny oscillations, but it will still stay. I will favor one-handedness, and it'll still stay there. So this is a possible explanation, but again, you can cook up examples where this may not be true. But the real answer, which always applies, more or less, which Bobby and I understood, was that the real answer is decoherence. That is, the interactions with the environment will break the phases or whatever you need for the tunneling, and the state will be effectively frozen into one of the isomers. This is mathematically expressed by the following fact. If you take the large D limit, so when in that formula that I showed you, when the here, when the D is much bigger than the V, you get to instead of damped oscillations like this, you get to overdamping, like you're familiar with from mechanics. And overdamping leads to the following behavior for the polarization vector. It gets frozen in the Z direction, and the decoherence parameter essentially stops the tunneling. And you get a frozen vector, which is frozen into one state. So the environment actually keeps one of the chiral isomers where it is. If you evaluate this thing for typical molecules, you get, again, extremely long time, so that in reality it's frozen into one of the states. And I think this is the real answer to Hund's paradox, although the other answers apply in certain cases also. So the collisions somehow interrupt the tunneling. And I'll explain in a minute one nice way of understanding this. So let's see if, one more minute. So now the second paradox, now it's getting worse. Now we come to Turing's paradox. This is something for historians of science. There was a story going around in my youth that one time at tea time at the Institute in Princeton, Turing said the following. If according to Copenhagen, when you measure something, you put it into one state of the measurement. So if you measure its position after the measurement, it's in one definite position, even though before the measurement maybe it was in some coherent state of different positions. So then Turing said, okay, well, if measuring it puts it in a certain position, why don't we measure it again? We'll put it back in the same position. If you keep measuring it rapidly, it'll never move. And there was a lot of confusion and unclear what this was and so on. This whole field is full of various mystical and philosophical ideas. But actually, Turing was right. And in fact, this Turing behavior is a consequence of our equation. Because if I make the D, which you can view as measuring the molecule or the spin system, repeatedly, that means I've got a big D, and in big D, I've got this limit, where indeed the quality, what I'm measuring, let's say the chirality, is not evolving or is frozen into its initial position and can't move or moves very slowly. So this is nothing mystical, it's just a solution of that p-dot equation in the limit of strong damping. So it's just that the environment stops the tunneling and it stays in the state it was. By the way, this is sometimes called the watch pot effect. I have to explain to the non-English native speakers that in English there's a saying, if you're cooking, making tea or something, and you keep looking to see if the water's boiling, it seems to never boil. The more you look at it, the longer it takes. And that's essentially what our equation is saying here. And as I say, in many practical examples, you will find that this parameter is extremely big, so that in effect the system is entirely frozen. And there's another paradoxical way of seeing this, by the way, that you see the D is more or less how often you're hitting the system. So you are saying that the more often you hit the system, the slower it relaxes, which is somehow maybe contrary to common sense. But that's because when you look back to the two barrier problem, let's see, where did I have this? No, I don't seem to have it. Okay. Anyway, it's the double potential well problem, and we are considering the tunneling through the barrier. Now, the normal everyday intuition that when you hit something, it'll relax faster is the classical intuition, which says that if you hit it more often, it'll jump over the barrier more often. That's true. But we are talking here about the quantum regime where the relaxation is through the tunneling. And in that case, it works opposite. That the more often you hit it, the less it'll tunnel. And one of our predictions in this old work with Bobby was that if you could do this experiment, you would find that at low, once you got the system cold enough so there was no barrier jumping, you would find this inverse anti-common sense behavior that the faster collisions led to less tunneling, less relaxation. So here's a simulation we did in some related problem where we started the polarization vector at some angle to the z-axis, so it was a coherent mixture of the two qualities, let's say left and right, or two kinds of neutrinos. And you find that if you have a big D, here's what happens. Very quickly, the length of the polarization changes. So the vertical axis is the length of the polarization vector, the amount of coherence. One would be perfect coherence, and with a big D, the length changes a lot, and it shrinks the polarization vector to the z-axis, the quality axis. And then once it's there, nothing more happens for a long time. That's the Turing paradox, or the watch pot. It's hardly decreasing at all, because we've inhibited the tunneling by the repeated collisions. Mathematically, it's just the big D from that precession equation. So now we come to the problem that everybody's scratching their head about. How much time have I got?
-1.
What?
-1.
Oh, I still didn't get to many of the... Oh, we started 10 minutes late.
Okay, can we keep it to 5 more minutes? Because
Give me 5 or 10 minutes.
Okay, we will have a very short discussion then. 10-minute discussion.
So why do the outside influences stop the tunneling? And after many discussions with many people, there was a nice, somehow the phases, tunneling is a delicate quantum mechanical process, and somehow the phases are getting messed up. One of the nicest explanations or suggestions was given to me by Michael Berry. Now, you see, so for tunneling in a two-state system, you have two levels which are almost perfectly degenerate. And now, if you're wiggling these potential wells, the degeneracy is continually being lifted. So you never have perfect degeneracy. And this will inhibit the tunneling. This seems to be, to me, one of the nicest explanations of what's really going on. That the constant wiggling of the potentials lifts the tunneling degeneracy. And now, that's nice because there's an even worse paradox. After Hund's paradox and after Turing's paradox, here's the one which is obviously crazy, but it took me for a long time to understand the answer. And this, I think, is due to this explanation about the wiggling of the potential wells. Let's have a particle or atom which is about to decay. So I have a bunch of detectors around, and these detectors are always observing that the atom has not decayed yet, the atomic level. So it's like the Turing paradox, which I claimed is correct. If I'm always looking at it, do I stop the atom from decaying? Well, this is obviously insane, but why? And I think the explanation is the following. I drew a picture because I forgot to put it on a transparency. You see what's happening? Let's consider the model of a resonance or of a decay, where you have one particle trapped in a potential well, one level trapped in a potential well, and it's transiting to the continuum, which, as you remember, you have to introduce the continuum when you teach the golden rule for these things. So what's happening is that even if you wiggle these potentials, you will always be degenerate with somebody. It's different than the two-state problem. So that, indeed, you get the common sense answer that observing if a particle has decayed doesn't stop it from decaying. At least in real life as we have it around us here. Okay, so what I don't have time to talk about where there has been most of the real sort of practical work in this field has to do with neutrino oscillations. As you undoubtedly have heard, neutrinos can oscillate between their different flavors. So an electron neutrino can become a muon neutrino and so forth. And so it's the same kind of problem. And this actually plays an important role, let's say, in core collapse supernovas, because the Fermi level is much lower if you distribute the neutrinos over two types of neutrinos, and therefore the pressure in the star is different, and you influence the progress of the supernova. So the question is, the damping, as we have worked out in generalizations of this, can perhaps stop the oscillations, which would affect how the supernova really evolves. So this is a big subject with many people working on it. Here's some references. I don't have time to talk about it. But it's actually one of the most interesting aspects, practical aspects. Here's another aspect. With a professor from Krakow and his students, we developed some studies of this for quantum logic devices. For example, the simplest one would be, we studied the realization with practical parameters with some squid people using the two states of a squid, where the so-called RF squid, where the electrons are going, a macroscopic number of electrons are going this way around the loop or going that way around the loop. And you have essentially a two-state quantum system. And you can have tunneling between the two states. And this is a realization of the knot of the information bit. You could say this is 0 and this is 1. And you can find the Hamiltonian using the capacitances and inductances of the squid, which if you've got some squid experts, they would tell you what you are and what they are. And we developed a series of programs dealing with these things, and especially the effect of decoherence. Because the important thing in the quantum computer is, of course, how long does a device like this stay in a coherent state and act like it's quantum. So we have a whole set of nice programs, and some of the references, you'll see some work we did with that. It's a very pretty system. What you see here is this squid Hamiltonian, here the two potential wells are exactly the same. And here I've raised one a little bit, and you see the two levels split a little bit. Here's the splitting. And this is the qubit, the two states of the squid, which can be in coherent linear combinations. And we imposed decoherence by wiggling these wells a little bit to find something we could do in the computer. We added a noise term to that Hamiltonian where the wells are being wiggled. And you can then derive a D parameter and see how this is evolving. And you can compare our simplified formalism with the true simulation of the quantum mechanical problem with these wells. And we find indeed close agreement with our simplified formalism with the D. And even we predict what the D is in terms of the noise. So this brings me to one of the next amusing things you can do with this system is to study the quantum classical transition. You see, say you've got this two potential well problem, and you start with your system on one side in one potential well, and these students made nice pictures in their programs, but you could even see the wave packets moving back and forth between the wells. But anyway, let's say you've started the system in one side of the potential well, and now if I move to the other configuration where I invert which well is higher and which well is lower, these levels will cross at some point, and it'll tunnel to the other side. So here you see the quantum behavior. I started in this state, I raised potential wells, and it tunneled to the other side. And indeed, in the pictures, the wave packet moves to the other side when you solve the Schrodinger equation with that Hamiltonian. So now, what happens now when we turn on the decoherence, as it's done by applying the noise to the potential wells? You will find, indeed, that you will stop the tunneling, and it'll stay on the right-hand side. That's because, as I keep saying, the environment or the noise stopped the tunneling. So you see, that's the quantum to classical transition. When you've got a lot of noise, it doesn't tunnel, it stays on this side. And when you don't have a lot of noise, it goes to the other side. So this is actually a way of measuring the decoherence parameter also. Because according to how fast you move these things past each other, which you can do in the practical case by varying an external magnetic field, you can see at what speed at what point in speed you have stopped the tunneling. So you've seen the quantum to classical transition. Okay, Laura's going to shut me up. Let me come to the thing which you might be interested in professionally. And this is what I like to call, I wanted to say decoherence stops the clock. But actually, that's not what I mean to say. I mean to say that when you have a lot of decoherence, there isn't any clock. And this is simple to understand, because what is a clock? It's something which has to move, or in particular, usually oscillating, right? A clock goes around once a day. So you need some oscillating system to have a clock. Okay, so the simplest clock you can think of is a system made of two, and the system, of course, has to have different energy states. If you don't have different energy states, there's nothing to oscillate. So let's go back to my original favorite thing, the K0 system. If I have two states of K0s with different masses, when I square the wave function, I will get an oscillating term. That's the clock. So with K0s, I've got a clock. Now, however, for this to work, the two mass states have to be coherent. You have to be able to interfere them to get this cosine term. Now, is there any known force or which interacts with different masses differently? I bet you all know what it is. So in a high or rapidly varying gravitational field, you will get some decoherence between the two mass states and the clock will stop working. And in fact, since gravity is universal, it'll do that to any pair of energy states. It's not just an accident. There's something intrinsic about this. So it seems to me that under conditions as we normally view the early universe, very hot random fields, you will indeed not have clocks anymore, even in principle. And to try to understand this a little bit, I did a calculation of my D parameter for this K-meson problem, and near the Planck scale, and here's what I got. As you would expect, it's inversely proportional to the Planck mass to some power, and is increasing with the temperature. And so naturally, it's only of practical relevance in this sense near the Planck scale. But I defy you to invent a clock which will work near the Planck scale in our usual understanding of what goes on near the Planck scale, unless in some way it's very cold. So you might wonder, if there's no such thing as a clock, what happens to all our concepts in general relativity? And of course, you can do the same for a ruler. In the same way, of course, to have a ruler, remember, to localize position, you need a lot of momentum states to lead to a well-defined position. So if these momentum states are getting incoherent, you don't have a ruler either. So this is a fine problem to think about tonight when you're going to sleep. How can you have general relativity without clocks or rulers? All right, here's a couple of more homework problems which I would like to see answered for myself also. This D, the decoherence rate, is a kind of dissipative parameter like the resistance in electricity. And, okay, let me just make the two homework problems here. In electricity, you have something called the decoherence fluctuation relation, where a resistance leads to a fluctuation in the current. So what is fluctuating when you have D? If it's a kind of resistance-like quantity. And I have some thoughts about this you can find in the references, but I'm not entirely satisfied with the answer. Another nice problem is that for our computer simulations, we put this noise term in the Hamiltonian, and a question you can obviously ask yourself, is that really equivalent to tracing over an environment? It seems intuitively obvious that sometimes it's right, but is this really a complete answer, and how do I show it? And if anybody has any ideas how to do this, I'd be grateful. And of course, final homework problem is how do we go beyond the two levels? We would like to really deal with the continuum, and at least in this very simple stuff I've been explaining, where you can do everything with your fingers and toes, we haven't really dealt with the continuum problem. Okay, sorry for being so long. Thank you.